Okay, did everybody have a chance to read the part of the text that we're going to be dealing with today? I unmuted everyone, so you can just...
Yeah, just a bit. Just it's just 2 pages, right?
It's understandable.
461 to 477. I've got them here.
Yes.
Okay. Yeah, so I was going to start with we're going to go over what I would have covered if I was kind of hoping to get to some thermochemistry this morning. But for some reason, these online lectures seem to take a lot longer than normal. I don't know, maybe because I talk more slowly or something, or we're actually learning more, one or the other. So I was going to start with that and then go over what it is we're going to try and do today, and then go to the page. Does everyone have the link to the page where we're actually going to be doing the lab today? It was in...
It's in that page. It's in that. It's in that paper, that document that you have right there, right? Right there.
That
one?
I didn't.
Should have that there.
I didn't get that one. Oh, hang on.
It's in, so you can go to Canvas and it's an announcement. I think it's like the third one down that basically just has like experiment 9 online lab, something like that.
Give me a second. I'll get it up.
Because we're gonna need that for later. Oh, come on up, Jerome. Come on.
Is it the one that says next chapter 9 or?
It's not the first one. I think it has online lab.
First online lab.
Announcements.
It has a PDF on it, right?
Yes, that's the one. Yeah, first online lab, Thursday, 3/26.
Okay, I got it.
Here. Yeah, experiment 9, determination in specific heat.
Okay, I have that open.
Okay, cool. Yeah, so we'll need that in a minute. So the first thing I was going to do is just go over the basics of what it is we're going to be doing today, and then we'll go to the site and play around with the simulation. It's really cool. I've been playing around with it my own self. So, but first I just sort of wanted to get into just the basics of what it is we're doing and how it leads into thermochemistry that we're going to be studying when you guys, when we come back to class. It's not like everyone's going to be having a really exciting spring break or anything, but continuing to hunker down. So one of the things I wanted to point out that's really, really important is that heat is not the same thing as temperature. It's something that we confuse a lot, but it's not the same thing. So let me get my pen up here. So heat is given in a quantity called Q. And basically what heat is energy. We'll find as we continue this chapter that there's basically only 2 ways that heat can be transferred from one place to another. One of them
for the lab. Is the guy actually doing the lab, or he's just talking about it?
All right, I'm going to have to go back to everybody. Hello?
How?
Oh dear. So I was going to ask, who can? So heat is one way that energy is transferred. Anyone know what the other method is?
I wouldn't do like physics. He hasn't said that.
Does it work?
It's work, exactly.
My mic is on.
Yeah, you can turn your mic off. Whoever's making all that noise. I kind of wanted to have a conversation with everybody. Yes, heat and work. That's really the only two ways that energy is transferred from one place to another. And so here we have two ways that heat can be transferred from a system to the surroundings. And it's a way that physicists look at energy. There's basically two places in the universe. There's where the reaction is taking place, and there's everywhere else. And so in this particular instance, the system is inside this container. So that we would say that that's the system, not even the container itself, that's part of the surroundings. But the liquid that's inside the container is the system, and that the rest of, everything else is the universe, or the surroundings. And so in this particular instance, we've heated up some water. Let's say we poured a cup of hot tea, for instance. I'm doing this experiment even as we speak. So the water, as you have noticed, drinking hot liquids for most of your adult life, it cools over time, right? And so that heat is lost to the surroundings. So at first, the temperature of the system is much higher than the temperature of the surroundings. Remember, that is temperature. That is not the same as heat. Temperature is the measure of the kinetic energy. Oh man, it's going to look. Kinetic energy of the particles or molecules in the system. So I would say that the molecules inside the cup are moving a lot faster than the molecules are in the surroundings. And that is reflected in the higher temperature. Now, as that temperature goes down from the system, from my cup of tea, it's releasing heat into the surroundings. And so it's losing heat. And so here we have heat being released to the surroundings. And heat is actually energy. And we measure that in terms of joules. We'll get into that in a minute. So the amount of heat in my cup is going down, and it's being transferred out. So we would say that Q is less than 0 because it's being lost. So in this particular instance, energy is going down. So I have energy that was high at the beginning. So here it was high at the beginning, then less at the end. And so Q would be less than 0 because it's losing heat. Now over here, I've got cold water, I've got ice water. And so the temperature of my system is actually lower than the surroundings. And you know that if you leave like a cup of ice water on a table or whatever, and you go away and you come back like a few hours later, that ice is gone. And the temperature has gone up. So what's happened in that particular instance is that you had slower moving molecules. The water molecules in the ice water are moving slower than they would be at higher temperature. And so the temperature is low. The temperature is lower than the surroundings. Over time, the temperature goes up to room temperature. So what's happened is heat has been absorbed by the ice water from the surroundings. And so now Q is greater than 0 because the temperature has gone up from 0 to 20 degrees or 21 degrees.
I just got an email.
Oh, okay. What's the email?
We're doing online throughout the semester.
Yes.
Isn't it? It says through the spring semester in an online or distance learning modality.
I got it too. Yeah.
Janelle!
Yeah,
Hi,
I got that
Natalie.
too.
Janelle!
We have people just joining now.
We had 10 people ever since we started. It was at 11 before.
Cool. Yeah, now we have 21. Much better.
Yay.
Yeah, so I'm just basically reviewing the difference between heat and temperature, because this is what we're going to be doing in our lab today. So when the temperature of our system goes down, we've lost heat. And so Q, which is heat, whoops, let me get my pen back. Q is less than 0 because it's been lost from the system to the surrounding. Over here, where we have the temperature's gone up, whoa, whoever's making all that noise could mute, please. Thank you. So over here on the right side, we have ice water with a low temperature become higher over time because the ice has been melting from heat being absorbed from the surroundings. So in this instance, Q is greater than 0 because now the melted ice has increased in temperature, absorbed heat, and now Q is greater than it was before. So when we lose heat and get cooler, Q is less than 0. When we raise the temperature, you increase the heat and Q is greater. Yes, Gabby. You have a question?
Yeah. Can I see the table again? Because I copied the one from the original lab manual, and I think the one you have here is different.
Yeah, it is a little bit different. Basically, just get rid of the first two lines. I think it had the mass of the calorimeter and the mass of the calorimeter plus water. So we're not going to be doing that. So you can just eliminate that. Just keep the rest. We'll go over it a little bit more once I get through these. Okay.
Okay.
All right. Cool.
We're only starting with mass of the water.
Yes, just going to be doing, because it's an idealized situation. In the real world, you would have to worry about the heat being absorbed by the calorimeter because it's the real world, and then you're going to be losing heat into all sorts of things. But in our idealized experiment, all of the heat is going to be transferred from one place to another without any loss. So much easier calculation to do. All right. So these are the units of energy you're going to be using. So the metric unit of energy is the joule. And you're probably familiar with calories because we measure food energy in calories. And it was once defined by the amount of energy you needed to increase the temperature of 1 gram of water by 1 degree Celsius was a calorie. And actually a food calorie is 1,000 of these. 1,000 calories or a kilocalorie. So some foods you might buy from like Europe or something have kilocalories on them. And in the US, they're referred to as calories, but they're the same. It's the same thing. But we're going to be dealing with joules. And the difference is this conversion here. So a calorie is larger than a joule. And there's another unit you may have seen. I don't imagine how many of you have been out buying refrigerators lately. Probably not too many. But if you buy a refrigerator or sometimes you something that either heats or cools something, it's rated in terms of BTUs. You may have heard of BTUs. They're called British thermal units, and that's equivalent to around 1,000 joules. But what we're going to be dealing with is like almost exclusively is the joule. Every once in a while, we may want to convert something to calories, but we're not going to be using BTUs terribly often. So someone pointed out accurately that there's basically 2 ways for energy to go from one system to another. And one is heat, and we refer to that as Q, and the other is work. We just refer to that as a small w. And so here, just a classic example of burning fuel in your car. Some of it gets converted to work, pushing your car along. But if you took that same amount of gasoline and just burned it to release as heat, it would be exactly the same amount of energy. So if we release it doing, some of it's going to do work, some of it's going to be released as heat. Basically, in our car, obviously we want as much of this energy contained in burning gasoline. We want that to be converted to as much work as we possibly can. That would be part of the efficiency of an engine. This is one of the reasons why electric cars are so much more efficient, because they don't generate heat. Petrol engine cars generate a lot of heat, as you probably know. I think only about 20 to 25% of that energy gets converted to work. The rest gets converted to heating up your engine. So that brings us to what we're going to be doing today in lab, is something called calorimetry. Now, right there, you can see that calorie is a big part of this, and this is actually how the amount of food energy in food is calculated. You dry down the food that you're going to be measuring. Let's say, Cheeto or something. You grind it into a really fine powder. You put it in a calorimeter, and we'll see what a calorimeter looks like in a minute. Basically, it's just a contained structure where you can burn something. So you take your Cheeto, you would grind it to really, really fine powder, and then you pass pure oxygen over it, and then set off a spark and burn it. And the amount of energy released from that Cheeto would be transferred into water surrounding where you've burned your Cheeto, and you'd measure the amount of temperature that water went up, and then you relate that to the amount of energy that was in your Cheeto dust. So the heat, which is lost in burning the Cheeto, is exactly equal to the heat that's gained by the water. And so that is how we can say that Q which is the same as what we're going to be doing in our lab today. So the heat that's in the metal, Q that's in the metal, is equal to minus Q of the water. So as one goes up, the other one goes down. So as the heat is lost from the metal, it goes up in the water. And so it always equals zero. That's the first law of thermodynamics, is that you can't create energy, you can't destroy energy. It just goes from one place to another. You just change the form of it. And so the energy that was in the metal, when you heat the metal, you've now added heat to it. Q has gone up. When you put it in the water, that heat is going to go down, and the heat of the water is going to go up. But at any point, if you measure Q of the metal and the water, when you add them together, you should get zero. So for calorimetry, we're measuring Q. And how do we do that? Well, actually, we're determining Q by measuring something else. So we measure a couple of different things. So we measure the mass of whatever it is we're changing the heat of. So in our experiment, there are going to be two masses. It's going to be the mass of the water, and it's going to be the mass of the metal. And so what we want to do is measure the mass of both of them. Then we're going to measure the change in temperature. That's what delta, if you remember, that's what delta refers to. Delta refers to change. So we're going to measure the change in the heat. And C is the heat capacity. Now the heat capacity is written down here on the bottom. It's the amount of heat that's required to change a gram of that thing, whatever it is, by 1 degree. That is the specific heat capacity. And water has a really high heat capacity. That's one. I'll show you some of the examples of other heat capacities in the next.
Mr. LeBlanc,
Professor?
Yes.
is your did you click on the link, and are you on the experiment?
Yeah, because you see your
we
PDF.
see the document.
You're not seeing the slides?
No, we're not seeing
No.
the experiment. We're looking at the PDF that you sent.
Oh, you can't see the slides. That's what I'm sharing in the meeting, are the slides. You can't see them?
Yes,
No.
we don't see it.
I don't see it.
You don't, oh,
I
okay.
only see the PDF.
Okay, let me pause this for a second. All right. Take that down. So is it gone now?
Yeah.
All right, let me go back. Okay, can you see it now?
Yes.
Yeah.
Oh, interesting. Okay, so you want to, should I go back a little bit? I can just start with this again. Just let me erase some of this stuff.
Yes, please.
Sure.
Yeah.
Let me erase this. Right, so the experiment we're going to be doing today is called calorimetry. And sort of, it's kind of obvious where the name comes from, for calories, right? Because this is the way that we measure the heat energy of food, or basically the heat contained in anything is determined by calorimetry. And so when we do a calorimetry experiment, what we're actually doing is measuring the amount of heat that's lost by something by measuring the amount of heat that's gained by the water surrounding that thing. And so one thing that we use to measure heat is something called a bomb calorimeter. Now, what a bomb calorimeter is basically something that burns, is a device that burns something at a very high heat. So I think I gave the Cheeto example. So if you wanted to know how much food energy there is in a Cheeto, you grind it to a very, very fine powder. You put it inside a bomb calorimeter where pure oxygen is flowed over it. Then you would set off a spark, which would burn all of the carbohydrates and whatever else is in the Cheeto. And that would then use energy, right? So the Cheeto would get hot from the burning. It would transfer that thermal energy to a jacket of water that's surrounding where you're doing it. Do it in a sort of basically a metal tube inside of a jacket of water. And as the metal warms up, it transfers the heat to the water. And we can measure the temperature of the water extremely precisely, like down to micro degrees. So we can measure extremely precisely. And so what we're doing is we're measuring the amount of heat that was in the Cheeto by measuring Q of the water, because Q of whatever it is we're burning or whatever it is we're heating. In this particular instance, in our experiment today, we're going to be measuring Q of the metal. So we're going to take a piece of hot metal and we're going to put it into some room temperature water. Now, the temperature of the metal is going to go down over time, right? It's going to cool. But the temperature of the water is going to go up. And what we'll find is that the two are equal and opposite, because energy in the first law of thermodynamics says that energy can't be created or destroyed. You can only change. You can only change it in one form to another. Like you could, in the Cheeto example, you're taking chemical energy and you're changing it to thermal energy. You haven't created or destroyed the energy. You're just changing it from one form to another. And the same thing goes here. So the heat that comes out of the metal goes into the water, and they're equal and opposite. So however much heat the metal loses is exactly the same amount of heat that the water gains. That's how we're going to do our calculations today. So it.
Professor, I have a question.
Oh, sure.
Can we control the energy?
Yes. I mean, you could change the temperature of the metal. You could put more heat into the metal. In fact, that's one of the things I want you to do in the lab today. So in the description, in the procedure, I give an example of, like, use this much metal at this temperature and add it to this much water at this temperature, but change it around and see if you get the same answer. I want you to for you to see that it's constant, that this heat being transferred from one place to another is always equal and opposite. And so if Q loses 100 joules, let's say if Q loses 100 joules energy, the water gains 100 joules in energy. That's how we can do this. That's how we can do an experiment like this, because the changes are equal and opposite. And so what we do in this particular experiment is we're going to be determining the heat capacity of metals. And what heat capacity is how much heat does it take to raise 1 gram of that substance by 1 degree C, or 1 Kelvin, which is the same thing, right? A change of 1 degree Celsius is the same as 1 Kelvin. The scales are the same in terms of the distance between each degree. So like the distance from 0 to 100 degrees Celsius is exactly the same as 273 Kelvin to 373 Kelvin. The difference is the same. So here we're going to measure a couple of different things in order to determine what the specific heat capacity is. We're going to measure the mass. So if we measure the mass of the metal and the mass of the water, if we measure the change in temperature of each one of them, and as remember, the temperature of the metal is going to go down, the temperature of the water is going to go up. And we measure the amount of heat that's lost or gained using this formula. So heat is in joules. So we have C times grams, so our mass is going to be in grams, times degrees Kelvin. So C is going to be measured joules per degree Kelvin. That's what C is going to equal. So basically, we're going to solve, we're going to measure grams, we're going to measure the change in temperature. Man, that's loud. Okay, I'm going to have to mute some. Okay. So we're going to calculate, we're going to measure grams in our experiment. We'll measure grams. We'll measure the change in temperature, and we'll use that to calculate the specific heat capacity. Right. So here's some of the heat capacities of some of metals and some other compounds. And you can see that water is really high. In fact, water is one of the highest heat capacities of any substance in the world. And that's why it's so good at cooling things, because it absorbs a lot of heat and it doesn't change its temperature very much. So that's why you see, it's in car engines to reduce the temperature of the car engine. You see it in like steel plants or any plants where they produce like molten metal and they need to reduce the temperature really fast. They'll dump it in some water because the water will absorb that heat quickly and not change as much in temperature. On the other hand, you can see these metals here. It doesn't take a whole lot of heat for them to increase in temperature because metals conduct heat and electricity very well. And so their heat capacity is going to be low because heat passes through them very quickly. Electricity passes through them very quickly. And the two of those things are related. So you can see down here, glass isn't a particularly a good thing to keep heat from leaving your house. So a lot of what builders do is have two sheets of glass with something in between them, like either air or if you have really fancy house, like nitrogen or something like that in between. So temperature doesn't pass through the glass out into the surroundings, so your house stays warm. You see wood does a much better job of insulating than a lot of these other things that you build houses out of. So let's do just a quick sample questions to get you familiar with the kind of things you're going to be doing today. So here we've got, if you have like really good cookware, a lot of them have copper on the bottom because copper has a low heat capacity, and so copper skillet will get the temperature much, much faster than one made out of aluminum, for instance. And so copper heat capacity is here. It takes only 0.4 of a joule to raise 1 gram of copper 1 degree or 1 Kelvin. So it doesn't take a lot of energy to raise the temperature. So how much heat do you need to raise the temperature of a copper from like room temperature at 25 to like 300 degrees C where you cook something? So you know the mass is here, and you know what the heat capacity is. Heat capacity is here. So all you need to do is figure out what's the change in temperature, and then you could figure out how much heat is required to do that. So let's calculate the change in temperature. So we start at 25 degrees C, and we went to 300 degrees C. So our change in temperature is 275 degrees. Now, we could use it 275 degrees C or 275 K. It's the same thing because it's a change. These two are equal to each other when it's a change in temperature, okay? So Q is equal to the mass, and I think the mass was 125 grams, times the change in temperature, which is 275 K, times the heat capacity. And let me go back and see what the heat capacity is, 0.387. 0.387 joules gram Kelvin. Now, I like to include the units because then I'm seeing if I'm doing the calculation correctly. So I've got joules in the denominator, grams in the denominator, grams in the numerator. I've got Kelvin in the numerator, Kelvin in the denominator. So now I just multiply 125 times 275 times 0.387. Let's see if we get, so 125 times 275 times 0.387. So I get 13,303. So how many significant digits should I have? You can unmute yourself and answer.
3.
3.
3, right, because there's three significant digits here, here, and here. So how I would express that would be 13.3 kilojoules, because it's 1, 2, 3, multiply by, divide by 1,000, 13.3 kilojoules. Yeah. So same answer. All right. So here's basically what, if we were in lab, this is the calorimeter we'd be using. Not quite as fancy as a bomb calorimeter. Basically, it's just a coffee cup. And here's the piece of metal you would have put in it. You would have put in a known amount of water and measured the temperature. So you'd have the mass of the water. You'd have the initial temperature of the water. And then you would put in a known mass of metal. And you'd know what the temperature, the initial temperature of the metal would be. Because how we were going to do the experiment is, so basically we take the piece of metal and put it into some boiling water, and then assume that the boiling water was 100 degrees C. We'd actually be, measuring the temperature of the water with a thermometer. So then you take that hot piece of metal, put it into the water, and watch this temperature go up over time. And when the temperature stopped increasing, you'd say at that point that all the heat has gone from all the increased heat that we've put in to the metal has gone into the water, and they've achieved an equilibrium. They're not changing anymore. If we waited for a lot longer time, obviously this temperature would go back down to room temperature, and all the heat would be lost to the surroundings. And that's how we would do the experiment. So this is pretty much the exact question you're going to be doing the calculation today. So let's go over how you would do that, because you're going to need to do this for your lab report. So here we have a solid, and we're trying to figure out what the specific heat capacity of the solid is. That's what you're going to be doing. You're going to be taking some unknown metals in the simulation, putting them into water. It's going to increase the temperature of the water. Then you have to go back and figure out what the heat capacity of that metal was. So here's the plans. So you're given the mass of the solid right here. You're given the mass of the water. Remember, we don't want volume, we want mass, because heat capacity is measured in terms of grams, not milliliters or liters. It's not volume, it's mass. So we put it into our little coffee cup calorimeter. Then we watch the temperature go up. And then it goes from room temperature here, this is the temperature which it started, to the temperature the water ended. One other thing we have to remember is, what was the temperature of the solid? We needed to measure that. And so we had the solid in some boiling water. So we measured that at 100 degrees. So we have the mass of the solid, we have the mass of the water, we have the initial temperature of the solid, we have the initial temperature of the water, we have the final temperature of the mass of the solid, and the final temperature of the water. That's a tricky thing to remember. One thing that trips people up is that the change in temperature is going to be different for the metal and for the water. So let's just go over how to do that. Let's just write down what we've got first. I didn't put that on the slide. So we have 22.05 grams of the solid at 100 degrees. We've got 50 grams of water. Okay. So we need to find the change in temperature of the solid and the change in temperature of the water. This is the thing that throws most people off at first, because it's not going to be the same. So remember, the solid goes from 100 degrees down to 2849. Now, the two are going to end at the same temperature, but they're going to start at different temperatures. So this is the change of my solid. Now, the change of my liquid is from 25 28.1 to 28.49. Remember, they're going to end at the same temperature. Start at different temperatures, end at the same temperature. So my change for the solid is negative, because remember, it's gone down. So I want to have the sign there. Negative 7151. Either K or degrees C, it doesn't matter. Now my change of the temperature of water is positive because it went up. It went from 25.1 to 28.49. The change in the water is much less, 3.39. And that's for two reasons. First one is that you have more water. There was 50 grams of water, and there was only 22 grams of the solid, whatever it was. So we don't expect it to go up as much. The other difference is the heat capacity of water is really big. And so it takes a lot of heat to change the temperature of water, where it takes only a little bit of heat to change the temperature of most solids, metals in particular. So now we set up that our Q of the metal equals minus Q of the water. So now we will, because whatever loss of heat by the metal is gained by the water. So they should be equal and opposite. So one is minus the other one. And so we'll just start putting in all of our different values that we know for metal and the water. So Q is equal to the mass times the change in temperature times the specific heat capacity, or the specific heat, which is what we're measuring here. And so for the metal, that is 22.05 grams times C, we don't know what that is yet, times the change in temperature, which is minus 71.51. That is going to be equal to minus, for the water, and our mass of water was 50 grams, times 3.39, it's a change in temperature. And the heat capacity of water is 4.184. It's just a number you'll remember, you'll either stick in your head or it won't. 4.184 joules per gram per degree. So you can see on this side, we have all the information we need. We have the mass, we have the change in temperature, we have the heat capacity. On the other side, for the metal, we have the mass, and we have the change in temperature, but we don't have the heat capacity. So basically what we're going to do is solve for C, okay? So what that gives me, 2.05 times 71.51. So I have minus 1576.8 C equals minus, and then I take my 50 times 3.39 times 4.184. This equals 709.2. So now all I have to do is divide each side by 709.2, and that gives me my specific heat. And so in this instance, it's going to be 1576.8 divided by 709.2. So my specific heat is 2.22. And so my units of specific heat are always going to be the same. They're going to be joules divided by grams divided by the change in temperature. So this is our specific heat or whatever that solid was. Is that clear how we do these sorts of calculations? It's basically it's algebra. There's so much
Like,
algebra.
just
So
out of
much algebra in
curiosity,
chemistry. Yeah.
so you did 709.2 divided by negative 1,500.
Oh, it's the other way. I'm sorry. You're absolutely right. I screwed that up. It's 1 over that. Yeah. I should have moved to 1576 over. Good call.
Yeah.
You can see it's really easy to make mistakes when you're doing these sorts of things. So what's the right answer?
Well, since they're both negative, the answer is a positive, so it's 0.44977. Well, what's the significant digits? It's
To be
let's see.
three significant digits, I think.
Yeah. Or no, 0.45. 0.45.
Oh, 0.45. Okay.
Yeah, not 0.48.
That makes more sense. That looks more like a metal. A metal, almost all metals, I think all metals have heat capacities less than 1. And you'll find that heat capacity is always positive. So that's why you need to watch your signs. That's why Q of the metal equals to negative Q of the water, because one, the temperature is going down, and the other, the temperature is going up. And so the signs of these will be opposite. So that's why we have the negative in there, because that cancels that out. Yeah, so we should have a positive heat capacity. Oh, and there you go. Yeah, 0.45. Excellent. That's the right answer. Okay.
So this is a heat capacity for the metal, right? The anode metal.
I'm sorry?
So this is like the heat capacity for the metal that we're trying to find.
Right. We just calculated the heat capacity for the metal, for the solid here, for T solid. So we know what we need to go on. We know what the heat capacity of water is. That's why we use water, because it absorbs a lot of heat, and B, we know precisely what the heat capacity of water is. We can measure its mass. We know the heat capacity, and so from that, we can calculate whatever the heat capacity of whatever it is we're either burning or heating, or whatever is transferring heat to the water, because we know these other things. So let's go to the procedure. Where is our procedure? So has everyone gone? Has everyone managed to make it to the website?
No.
I'm here.
Yeah, go. You should have the PDF from the determination of specific heat. It was in the announcements. If you don't have it, yeah, just take 5 minutes and go find it. Because it has the link there to actually run the experiment. I don't know if I could actually share a link out from this. I don't know if I can. You can't copy and paste from your screen, can you?
You could do print screen, and then that copies your screen. Just hit Control V afterwards.
And then you can. Is that hyperlink still active if you do that?
No, it just saves
Oh,
your.
but you
screen as
can
a PDF.
you can copy and paste it into your browser.
Yeah.
Okay. Yeah. If you want to, yeah, that's a good shortcut if you want to do it that way. Yeah, I might as well just go to the website, because that's basically all we're going to, because all the rest of it is just based on what the website looks like. So I'm just going to go to that. So Here it is. So this will what will pop up when you get to that site. So we want to click on experiment.
Professor, I think the
Screen's chosen again.
yeah.
Oh, is it? Okay. Let me. How about? What about? Can you see it now? Oh, let me pause. Oh, there we go. Can you see it now?
No, it's still the same
Not
screen.
really.
Hmm. Let me try this. Is that working?
Yeah, it's working now.
Okay. Yeah, I guess I think with everybody in the entire planet using the internet now, things are tending to freeze and then coming back. So we may have to deal with that a little more than we usually do. So you can, yeah, you can either get the web page from here or find it in the original PDF from Canvas. But it will take you to this page. And we want to click on the experiment tab and go to run experiment. So it leads you to two devices. One you'll be familiar with, one other one you won't. So the one on the left over here is obviously a balance. Oh, shh. Cammy. Jerome. Excuse me just for a second. You're going to run into that when you got doggies at home. So
I forgot my lab glasses at school. I hope that's cool.
I don't know.
You want us to wear them?
I don't know, man. Yes, this is dangerous. We're going to be dealing with hot things. So we got our balance on the left, and that weird looking thing on the right is actually a calorimeter, much fancier than the coffee cups we would have been using. So what we're going to do is we're going to first, on the left, we're going to measure out the mass of a solid. Okay, so we click on solids, and we'll just choose one. The first you have tin and silver, copper, iron, and aluminum. So they're all going to have different heat capacities. And so let's just do tin first. And then you can pick a mass, and that's on the slider here. So I'm going to pick, see a little piece, big piece, little piece, big piece. So let's take this, might as well use a large amount. Let's say 50 grams, okay? And then we're going to raise the temperature of that metal. And we can pick whatever temperature we want by sliding it over. I figure might as well make it a big number at first. So we'll heat it up to 200 degrees Celsius. And if you want to see what the specific heat of the tin is, you just click right here. And you can see the tin has a really low specific heat. In other words, if you heat up tin will heat up very fast. Tin also melts at a really low temperature, so you got to be careful about that. So yeah, you add just a little bit of energy to tin, and its temperature will rock it up. So now we're going to choose a liquid to put that in, and we generally hit next. So then you can see the liquids light up. So which liquid are you going to choose? And you don't have to choose water. You can choose something else if you want. But figure water, we know what the heat capacity is. Ethanol, you can look up what the heat capacity is if you want to use ethanol. But water, we'll put that in there. We'll take a mass of water. Let's say, let's say 150. Make it 100, 150, 200. Remember, it doesn't really matter as long as you make a note in your lab book of what the masses are. So that'll make a difference into how much heat is transferred. And the temperature, you can just leave it at 20 degrees. No, you don't really you don't really get to choose. So the temperature will be at 20 degrees or room temperature, and you can show the specific heat. Oh, so if you want to use ethanol, you can see the specific heat of ethanol is less. And so if you heat up ethanol, the temperature will increase more. That's why we use ethanol in thermometers, because it expands, it changes more than water would. So you pick either one. Usually we're going to use water because we use water in the regular experiment. But you can use ethanol if you want. It doesn't really matter. So here's our specific heat again, 4.184 joules per gram per degree. And if you notice, if you're paying attention during the lectures, you'll see that this heat capacity is exactly 1 calorie. So 1 calorie is 4.184 joules. That's where that number comes from, because it takes 1 calorie is the amount of energy it takes to raise 1 gram of water 1 degree. So that's actually the heat capacity, is 1 calorie. So now that we got our liquid, we have an amount of liquid. Let's go back. Let's say we'll fill it up, and you can see the thing filling up with water when we do that. Let's say we got 150. Make it a nice round number. So we're going to take our solid, which is 50 grams of tin at 200 degrees Celsius, and we're then going to drop it into the water and see what happens. So we go to next. Now we're going to run the experiment. And so there's 2 things you can look at while you're doing the experiment. One, you can look at the graph. We'll show you how the temperature is changing over time, how the temperature of the tin is going down, how the temperature of the water is going up. And you can see what's actually happening in the water. What's happening? You can see, do the water molecules start to move faster as the heat is being released? You can see that happening in real time. So let's just hit start. So the tin gets dropped in. And you can see the tin molecules moving a little more quickly and then slowing down as the temperature comes down, and the water molecules moving a little faster than they were before. And also on top of the calorimeter, you can see the temperature changing over time. And it finally stops, and the temperature we have here now is 23.06. So what you would do is you would write in your lab book, the initial temperature of water was 20.00 degrees. The temperature final of water was 23.06 degrees. The initial temperature of the tin was 200 degrees C, and the final temperature of the tin is 23.06. So to calculate what the heat capacity of the tin, you take the heat capacity of the water, 4.184. You take the change in temperature, which is 3.06 degrees, and you take the mass, 150. And then from those 3 things, the mass, the heat capacity, and the change in temperature, we calculate Q. Q should be in joules. That change, positive change, should be exactly equal to the negative change of the tin. And the things you know about the tin are the initial temperature, the change in temperature. So you know the change in temperature of the tin and the mass. And so you can calculate the third thing. You can calculate what the heat capacity is. Okay? So what I'd like you to do, then we just reset everything. You can run each one of these solids: tin, silver, copper, iron, aluminum. And I think what I mentioned in the lab procedure was take like 50 grams, heat them to 200, and then put them at 100 grams of water at room temperature, and then measure the change. So do that. Do the same thing for all of them. And then change it, then do it a second time and change the numbers however you want. And change, you can decrease the temperature of the metal, you can increase the mass of the metal, you can increase the mass of the water, you can decrease the mass of the water. You can make them whatever you want, and then do a second calculation of Q and a second calculation of the heat capacity, and you should get exactly the same thing. Okay, so on your results, you should have an average of your two results, what the Q was, what the heat capacities were. And you can put the results of your second experiment just in your results. Just give me, what you changed the conditions to, and then the calculation for Q of the metal. Then when you come down to the unknown metal, when you've done all of those, you go to the unknown metal and you put in, just do exactly the same thing, but it's not going to tell you what the specific heat is. So we'll take a certain mass of it, we'll heat it to a certain temperature. You're not going to see what the specific heat is. Well, you shouldn't see what the specific heat is. You need to calculate it. Well, this tells you what you should get, right? You should get that. But what you need to do is, so your calculation at the end should equal this, and then by looking up what the specific heat is online, you should be able to tell me what metal it is, okay? Because each metal has a very specific heat capacity. So we would say that that's an intrinsic property, because it doesn't matter what the mass is, and it doesn't matter what temperature you raise it to, you always get the same specific heat. And that's an individual property for each individual metal. So any questions on how to do this experiment?
So we have to do 2 trials of each metal.
Yeah. Yeah, one with the conditions I suggest, and then the other one however you want to do it. You can change anything you want. And just show that you get the same result for C, for the specific heat.
So how do you find the specific calculated specific heat again?
All right, I think I can throw up a screen. Where's my screen? Damn it. No, maybe I can just write on this screen. Okay. My pen's not coming up this time. Oh, let me just go back to the slides. Everyone see the slides, or?
Yeah, all right, we see it.
Can you see that? Okay, let me. Oh, damn it. Anyway, for some reason I can't change I can't erase. Oh, probably because I'm not in this mode. Okay, now let's go back. I think, yeah, here we go. Yeah, now I can erase some stuff. Oh, no, actually I can't. Never mind. So here from calorimetry. So Q, which is our heat, equals C, the specific heat capacity. Now I can highlight things, so let's do that. So C is my specific heat capacity. M is the mass in grams. So you determine what the mass in grams is in the experiment. You can put whatever mass you want. And then measure the change in temperature. Now the change in temperature for the metal will be negative. It'll go from hot to cold. So that will be negative. So you'll measure delta T. You'll put in whatever M you want, and then you'll be able to measure Q from the water. Now remember, Q, you're going to be calculating for the water, because with the water, you're going to know all of the variables. You're going to know the mass of water, whatever it is you put in. You're going to measure the change in the temperature of water, and you're going to know what the heat capacity of water is. Heat capacity of water is always 4.184 joules per gram per Kelvin. So you use this to determine Q. Heat capacity of the water, the mass of the water, the change in temperature of the water. That gives you Q in joules. So then remember that whatever Q of the water was is going to be equal and opposite to Q of the metal. So Q of the water will be positive because it went up. So you put a negative sign on that, and that equals the Q of the metal, okay? So for the metal, you're going to know the mass, you're going to know the change in temperature, and from that, you're going to calculate C. Does that make sense?
Yeah.
Equal.
I've wanted to ask, for the final temperature, remember that you showed us like 23 point something. Is it the final temperature for the metal, or like both the same metal and the water, or just water?
Oh, which on the slides here?
No, on the experiment that you show us.
Okay. Okay. Oh, here on the actual experiment?
Yes.
Okay. So if we do this experiment, let's go next. So our metal is 200. Can everyone see the experimental page again?
Yes, for me at least.
Yes. Okay.
Yeah, we can hear it.
So I've got my solid. I take my liquid, and I put in how much mass I want. Let's say 100 grams.
Does it matter?
Nope. You can put as much mass as you want. It doesn't matter. So I just suggest the first time you do it, I have some suggested conditions. But in the second run through, I want you to change as many things as you like. Because what you'll find is that your calculations, your Q will be different because you have different masses and different temperatures. But your C, the specific heat, should be identical. It should be exactly the same. So in this instance, let's do this experiment. So I got my mass, I got my metal, I know the mass, I know the temperature. My liquid, I know the mass, I know the initial temperature, and I know what the specific heat of water is. It's always going to be 4.184. All right, then I will start the experiment. So the hot metal goes into the water. Now remember, the change in temperature of the metal is going to be much greater than the change in temperature of the water. Because look, you see the water is the black line. That temperature is hardly changing at all, right? It's only going up by a little bit. So the change in temperature of the water went from 20 degrees. You can see down here, that was the initial temperature of the water, was 20 degrees. The final temperature of the water is up here, 26.36.
Oh, so the 26.36 is the final temperature for just water?
No, for both. Because remember,
okay.
Because the metal is in there. See, the metal is in the water. And with
okay.
So the temperature of the metal and the temperature of the water will be the same. At the end, temperature, all the heat coming out of the metal will have gone into the water, and they'll be the same temperature. And then eventually, they'll both decrease to room temperature, but they'll stay the same.
Oh, so the final temperature will be the same, but we'll have the same different initial temperature.
Exactly. So you can see that the change in temperature for water is only 6 degrees. See, it went from 20 degrees to 26.36. So the water only went up by 6.36 degrees. That's it. Very little. But the metal changed dramatically. The metal went from 200 degrees to 26.36 degrees. So it changed more than 170 degrees. The change in temperature of the metal is very dramatic. And the reason for that is the metal transfers heat very, very quickly. And so it goes from a very high temperature to a low temperature very fast because its heat capacity is very small. That's the difference. That's why water, like I was saying earlier, that's why water is so good at cooling things, because a little bit of it absorbs a lot of heat and doesn't change temperature very much. Yeah. So when you do these calculations, remember your delta T for the metal should be much greater than the water, and it should be negative because it went down. The change is negative. It went from a high temperature to a low temperature, whereas the water went from a low temperature to a high temperature. It's positive. That's why we have the negative sign. Q metal equals negative Q water, because one went up and one went down.
Also, like we can assume that like when we're getting the final result for the Q, we can assume that like both of them are the same, right? Like except the sign's gonna be like positive and negative for the Q.
Yes, the Q water equals Q metal, but negative. It should be equal and opposite. Because remember, Q is heat, and the metal is losing heat. It's negative. When we say a system loses energy, it's negative. So it's a negative value of Q. But water is increasing in energy. It's going up. And so that Q for the water is positive. But they should be equal and opposite. So negative Q water will be the same as positive Q for the metal, and the other way around. You can put the negative sign on either side, it doesn't matter. Just one is negative, the other is positive. Any other questions about the experiment?
Sir, I have a question.
Sure.
So the table in the lab manual, is that for just one metal? So do we have to make like multiple tables like that for every metal?
No, let me go back. So
I'm kind of confused on like the table.
Everyone's confused. I'm confused myself.
Initial temperature.
So can you see can you see the PDF now?
Yeah.
Oh,
yes.
God.
Okay. So basically, sort of what I'd like here is instead of trial 1, trial 2, trial 3, have metal 1, metal 2, metal 3, right? And so you have 7 of these. You'd have like tin, copper, aluminum, whatever. I can't remember what the other metals were. So then you'd have the mass of the water, the initial temperature of the water, which will be 20 degrees, mass of the metal over here, of the metal, whatever it is you started it as, and then the final temperature. And then you calculate what this heat is. Okay? So you would have 7 columns here. Metal 1, 2, 3, 4, 5, and then unknown metals 1 and 2.
And then you said for each known metal, you want one that with the same settings as the first one that we just did, and then a second one with different settings.
Yeah, I think I think I suggested 50 grams of metal at 200 degrees, and then 100 mils of water, or 100 grams of water.
How many trials are we supposed to do for each metal then?
2.
Oh, just 2. So like a total of 14.
Yes, but you can just put the averages in your averages in the table. But I would like to see you can make I don't know 14 if you want, but I just wanted an idea of what you changed the conditions to for the second one. Maybe so maybe you can have like 2 trials for each one.
Okay.
Or you could just show it. You could just show me an average and just give in the results section. Just say how you changed the conditions and what you got for your specific heat. Any other questions?
Yeah, what the hell?
What kind of question is that?
Why do you hate us?
Oh, I just have to. It's just, it's just my way. I love you guys. You know that. We're doing the best we can here.
Mm-hmm.
That's you, isn't it, Rachel? I can tell.
It's his
Yep.
job.
Yeah, well, hey, much easier doing this experiment than doing it in class. You don't have to worry about burning yourself. You don't have, you're not going to have big pots of boiling water all over the place. And you're going to get the same answer every time. So your percent error should be 0. It's not possible to have error here. So that means you care. So if there aren't any other questions, I was going to go over the lab test. Someone suggested this morning that we should go over the lab test.
I have
We
a
can definitely
question,
do that. Yes.
but it's not for this lab. I'm talking
Okay,
for the
no problem.
aspirin lab. When is it gonna be due?
If you didn't do the aspirin lab, it won't be due.
Never.
Yeah.
Oh,
Yeah,
Oh,
because
okay.
only my group did the aspirin lab. The other group
Oh.
didn't get to do it.
So when is it due then?
Oh, probably I don't know.
why? No, why?
No.
I could make it next week if that's okay.
Oh.
I can change it to next week. I think it was due today, but I can change it to next week.
Yeah, that sounds good.
Okay.
Okay.
I have another question.
Yes.
For the second like run with the same metal, would you rather us change the mass of the metal or the temperature, or the initial temperature?
Change as much as you want. You can change the mass and the temperature. Change it all. I just want you to see that no matter what you change, you should get this. Whoa, that's loud. Whatever that is. You can change whatever you want, and you should get the same heat. You should get the same specific heat number. Q will be different, but the specific heat, C, should be the same.
What were your conditions again?
Oh, it's in the PDF. It's if you go to Canvas, it's I think it's in the announcement.
Basically, it's just maxed out the grams, max out the temperature for the metals, and then 100 grams of water, and that's it.
Yeah, so it's 50 grams of metal, 200 degrees, and 100 grams of water.
And then you just run the same thing over and over again for each metal.
For each one, yeah.
And then for the second trial, and just to clarify, for the second trial, when we get to change whatever we want, right?
Mm-hmm.
We can just change as much as we want. Okay, gotcha.
Yeah, change everything if you want. That's fine.
Okay.
The first one we did was 100 grams of water or 150 grams?
I suggested 100, but if you want 150, that's fine. You can. These are just.
I thought we did 150.
Yeah, I think the example we did before was with 150. I just suggested 50 and 100 because it makes the math easy. But if you want to use like 137 grams and to make the math more difficult, feel free.
Professor, by the way, where did you post this PDF? Because I can't find it online right now.
It's the third announcement down. And I think the announcement just says like experiment 9 online lab or something like that. What I'll do is that I'll just post it. Okay, I'll just post it on the main page so you don't have to find the announcement. Is that cool?
Yeah, that itch.
Or I could send it in an email to everybody too. How about that? That might be the easiest thing to do. Just send it to everybody in an email.
For the water, I kind of noticed that it doesn't I don't know, maybe it's just me. Doesn't let you change the temperature of the the water, or is it just
No, it doesn't. Yeah,
No, the temperature is always going to be 20.
yeah.
Okay,
The
I
starting
thought I was crazy.
temperature is
Okay.
always going to be the same. Yeah.
Okay. Thanks.
It doesn't let you change the initial temperature of the liquids. You can change the initial temperature of the solids because that's where the Q is coming from. I mean, all the change is coming from the solid.
Wait, so does that mean that for each metal, okay, so for the first trial, right, where we follow the directions on the PDF, right?
Mhm.
Does that mean that the mass of the water, the initial temperature of the water, mass of the water, the mass of the metal, and the initial temperature of the metal is all going to be the same because it's going to be 50, 100, and 200?
Right.
Okay, gotcha. And then the only thing that should be different is just the final temperature.
Final temperature should all be different
Gotcha. Okay.
because that will reflect because if the only change is the heat capacity for each one,
Mm-hmm.
will show you immediately that the change of the heat capacity is responsible for the change of the temperature. If everything else is identical.
Got it.
Man, a lot of stuff going on in the chat. So if someone want to keep me updated on what's going on in the chat, I should be
All right,
aware.
let's see what they say. I think they're just talking to each other. They're talking about
the lab, like how many
yeah.
trials to do.
Okay.
Yeah, they're just doing that.
So is everyone clear and how to do the? I think what I'm going to do, and because some people have, some don't, I'm just going to send it out in an email. Just send out a mass email to everybody. And then,
And maybe in future,
if you have it already,
like,
that I should do that way in the future too.
yeah. Well, personally, I have teachers who like they send out an assignment, and then when you press on that assignment, there's a PDF where you download it and then turn it in.
Okay.
So maybe like that. I don't know. Just play around with it, I guess. Just
Okay.
whatever floats your boat.
Yeah. Well, I mean, it doesn't. It's not for me. It's for you. So
okay.
you
But
guys
I'm
want to
just-
get it. I mean, I thought maybe, just putting it in an announcement, if everyone checks the announcements, then it would be there and you wouldn't have another, stupid email to read. But maybe it's just, it's the best because you can skip over emails,
Mhm.
So, but if
Or maybe you could post
people-
it under where the original lab manual was, so it's like all in one place.
okay. Or I could even make a new folder with like online labs and just then put it in there. How about
Yeah.
Yeah, I think
Yeah,
that's
that works
better.
too.
that? Okay. I'll do both.
Is it just my computer, or when you get to iron, the mass of the water doesn't let you go over 90 grams?
I don't know. Let's try it.
Also, Professor, there should be 0% error, right?
Should be.
For everything, right? Yeah,
Should be.
people were asking about that too.
Maybe there is. I mean, maybe the simulation is designed to throw you a curveball, but so let's reset. So you said iron, something
Yeah.
weird happened when you pick iron?
It won't let me change the mass of the water past 90 grams.
Okay. Choose a liquid. Next. Water. No. Maybe it says something to do with the mass? Like a really tiny mass of iron or something?
Well, no, my mass is 50, temperature is 200. So I don't know why it's not letting me change it. It's letting me do it for all the other ones, just not this one.
And it's letting me do it too. So maybe you broke your computer. or
Probably.
you could always refresh the page. But
Yeah,
even that should give you a result. So all right. So is there any if there's nothing else about this, we can look at the lab exam if you'd like. Would that be good?
Yeah, go ahead.
Wow, that's the sound of someone who's excited. All right. Let's see.
I'm multitasking.
There you go. Lab test number 1. All right, so can everyone see the page? Should I
Yes.
All right, so I got it refreshed. So it's there, everyone can see?
I
Okay.
see the first problem.
Yep, so we got the first problem. Everyone pretty much got this one. The only problem that some people had, and you see I had a problem with it myself, is that there's 4 significant digits to the density. Because there's 4 significant digits to the final volume of the water, and there's 4 significant digits to the mass. So there should be 4 significant digits to the density. So the average density was 2.707. And then, so that identity of the unknown metal is aluminum. It's closest to aluminum. And I think one problem that I had a lot of people make a mistake with this last trial. I don't know why, but this last trial, a lot of people got this weird result where they got like 9 mgs per mil or something. I don't know where that came from, but like 4 or 5 people got that. And so their average density was way off for whatever reason. So then the percent error, you see, even I made a mistake here. There should be 4 significant digits here. So the percent error is really, really low. And the range is around, it's between, with 4 significant digits, it's like around 3.5. And with 3 significant digits, it's around 4. So it's just whatever the highest result was, whatever your lowest result was, and you divide that by the average. See if I can get a pen going here, or a pointer or something. Oops. Pointer. Oh, annotate. Here we go. Here we are. All right. Yeah. So you should have got an answer somewhere around 3.5 or 4%. So for the alum lab, one problem some folks had. Oh man. Now I don't have control. Oh, I need the mouse back. Here we go. So the only thing to worry about here was that the original mass of the aluminum is right here in grams, and you just convert that to moles. Here's our number of moles. And then I've even given you the molar mass of alum. That's written up here, 474.41. So that tells you how, if you got 100% yield, if all of that aluminum got converted to alum, you can see from the balanced equation, there is 2 moles of aluminum for every 2 moles of alum. And so it's a 1-to-1 ratio. So for every mole of aluminum, I should make 1 mole of alum as well. So that's the same number of moles of aluminum, should be the same number of moles of alum. And so you should just convert these moles back to grams, and your yield with 3 significant digits, because we have 3 significant digits for the aluminum foil, is 13.3. And then your percent yield is, if this was your actual yield rather than 13.3, you should get like 54%. I think most people got these ones correct. All right, so let's go to the next one. So chromatography lab. I think the only mistake people made on this one was just not being able to measure. That's a bit of that is on me. What I'm going to do next time is actually have a ruler next to, I'm just going to put a ruler here. So you know, just have a ruler right here with the numbers on it, so you'd be able to measure it without bringing your own ruler to class or whatever. So the distance from the spotting, and it's this is our baseline down here. So here's our baseline at the bottom. So the distance from there to the solvent front is 43 millimeters. And so we just measure the distance of each one of the spots, should be less than 43. And whatever that distance is from the baseline here to the spot, we divide that by 43 millimeters, and that gives us our RF. Okay? And so they all should be less than 0 or less than 1, and they shouldn't have a unit because we're dividing millimeters by millimeters and leaving us with no units. So if you calculate all the RF values for the unknown spots, get like around 2.27, 0.52, 0.52, and 0.83, or 3 significant digits if you measured it that accurately. And then the identities are metal and iron and nickel and copper. You got a point for each one of those. And then the question on the bottom was, if you let the chromatograph continue after the solvent front went over the top, you would underestimate or overestimate RF because you underestimate the solvent front. The solvent front actually went further than you can measure. So the solvent front went to the top, and realistically, it kept going. And so because you're dividing by the distance of solvent on the bottom, this is an underestimation on the bottom, under. And because that's an underestimation, when you divide by an underestimation, you get an overestimation as a result. So that's sort of the answer I was looking for. It didn't have to be said exactly like that, but basically that's what I was looking for. So if you just said it was overestimated, but you didn't give me a reason, you lost a couple of points on that because you have to have a reason. All right, let me go to number 4. Now this one you had to remember a lot of stuff about doing that lab. That was a very elaborate lab. There's a lot of moving pieces in it. The first part is fairly straightforward, and then the second part was a little trickier. There's a couple of ways to get to the answer. So the first part was just looking for how much water is in there. And so let me get a bright color. So this was the amount of the metal sulfate, and this is the amount after you dried it. And so the difference in these two masses is the difference in the mass of water. So basically you just had to subtract those two, and that gives you the mass of water. So, my mouse, there we go. So here's my mass of the sulfate, 0.693. Here's the mass of the water, without water, 0.319. So the mass of the water is the difference, 0.374. So the mass of the water divided by the total times 100, the mass of water, so percent. So it's 54%. And most people got that one. Some people made it more difficult for some reason, but yeah, 54%. Now the tricky part was remembering how to calculate the amount of sulfate. Now, a lot of people made the mistake of assuming that if 54% of the metal sulfate hydrate was water, the rest of it must be sulfate, forgetting that the metal's there. I mean, it is metal sulfate hydrate. So we need to separate the metal from the sulfate in order to figure out each of them separately. And remember, we did that by precipitating the sulfate by adding barium salt. So, because barium plus sulfate, you put them together and they precipitate it out. And so for that, we've had to figure out what the mass of the filter paper plus dry barium sulfate sample was. Subtract the mass of the filter paper, and that gives us the mass of the barium sulfate. So the mass of the barium sulfate is 0.166 grams, the difference between the filter paper and the total. So 0.16 grams. Question?
Out of curiosity, yeah, I have a question about the lab.
Mm-hmm.
So so when we try to use our own measurements, right? So
Right.
say like does each measurements should each of the metals have their own fixed measurements?
I don't know. You could make them whatever you want.
Oh, okay, all right, never mind then. Thank you.
Yeah, you can change. That's the whole point. Is that you can change any of the. You can change the mass. You can change the temperature.
So yeah, oh, okay. I just want to make sure, because I was just wondering, like, if say like tin and silver should have the same amount of mass, or should they have different masses?
You can make it whatever mass you like.
Okay. All right.
Yeah. The whole point of doing that exercise is that you should see that no matter what you change the temperatures or the masses or anything, you should get the same heat capacity. The specific heat should always be the same, no matter what conditions you change. That's the sort of the point I was trying to make.
All right.
Okay.
Mm-hmm.
All right. So get back to this. So we figure out our mass of barium sulfate. Then we just calculate how many moles that is. So we have the molar mass of barium sulfate here. That's why the molar mass was given. So that gives you you can calculate the number of moles of barium sulfate. And since it's a 1-to-1 relationship between moles of sulfate and moles of barium sulfate, that's the same number of moles of sulfate. And then you use the molar mass of sulfate, which is 96.06. That was given as well, grams per mole. That will tell you how many grams of sulfate there was. And so you take the grams, you figure out how many grams of sulfate that is, divide it by the total, and you should get a little less than 10%. Okay? So you should have 54% for the water, and I think it was around 9.8% for sulfate. And you need to determine that by calculating the moles of barium sulfate. That's how we did the experiment. So let me clear those and go down. So what's the percent yield if your unknown is this particular metal sulfate? So what you needed to do was use that amount of metal sulfate or amount of sulfate you used initially. So from the first part, from part A, like how many moles was that? And I had this many moles of sulfate. You didn't even need to convert it back to grams if you didn't want to. Because if your unknown is this, you're given the original mass. What is it, like 0.693 grams? Figure out how many moles of that metal sulfate there is, which is this many. You got this many moles of sulfate that you recovered. And so your recovery would be the moles that you recovered over the moles you were given. And you should get 33%, about 1/3% yield. Any questions on that? That was the question I think that gave most the people the hardest time. Was that one, because there's a lot to calculate in there, and a lot to remember. Let me clear. All right. So complete balanced equation for hardly anyone got this right. So the complete balanced equation, just had to remember that when that dissolves in solution, the sodium ions are released, sulfate ions are released, and water is released. So instead of, so you get 2 Na plus, you have 1 SO4 minus 2, both aqueous, they should have aqueous at the bottom, and 10 moles of water, liquid. So many people put water as a gas. I don't know why. I think if you dissolve a hydrate, it turns into gas, but it doesn't. So let's go down to the aspirin lab where, yeah, sort of things went wrong. So the aspirin lab. So the wavelength that should be used is the wavelength right here. Right here at the very top, because that's wherever the highest absorbance is, that's the wavelength you should use. So just follow it down to the bottom, and anywhere between 355 to 380, just eyeballing it, and anywhere around there is the right answer. And so the reason for that, and a lot of people just said because it's the highest, which okay, fine, but you need to explain why that's important. And the reason is because it gives you the most sensitive detection. So the highest absorbance gives you the most sensitive detection at low concentration. That's the main reason. And if you want to look at Beer's law, which is here, the absorbance is equal to the C concentration times this, what we call the molar extinction. And if this number is really, really high, then your absorbance will be higher for a low value of C, low value of concentration. So that's the reason. All right. Now, some of the calculations were a little tricky. So to do this calculation, basically you just take the equation of the line that's drawn. So this is the equation of the line. Y is our absorbance. X is our concentration. So you just plug those into the equation here and determine what the concentration of your unknown is. So if your unknown concentration is this, you plug in the values from the line. So your concentration will be 1442.7. And then here's your y-intercept here. Move the y-intercept over to the right side, divide everything by this, and this is the concentration you should get in molarity, because the concentrations here are given in moles per liter or molarity. And so it's 0.00452, or you could have also said 0.0452 millimolar. It's the same thing. So that is the concentration of the dilute sample. Now, what people forgot, or a lot of people forgot, is that was diluted 20 times before we put it in the spectrophotometer. So if we want to calculate what the more concentrated solution was, we need to multiply that by 20. So we figured out that it was 0.00452 molar, but we need to multiply that by 20 to get the concentration of the original, right? Because we took, was it 5 out of 100? So we had 100 in our graduated, in our volumetric flask, and then we took 5 out. And so if we want to know what so we did a 20-fold dilution in order to do this calculation. So we multiply that by 20. And so our concentration in the 250 mil flask is 20 times higher. So it's 0.00904. So it's gone up by 20. So in order to figure out how many moles were in that originally, we multiply by the mass of aspirin, which is 180 grams per mole, figure out how many moles, and the concentration times the volume. That's how many grams. It's grams over moles. And what we should get is 0.4068 grams. And then when we change it to milligrams, 1, 2, 3, 407 once we figure out there's 3 significant digits. There's actually only 2 significant digits, but I sort of let that one slide. So either 407 milligrams or 410, either one of those is correct. Does it see how to do that? Any questions about that? You can either like digitally put up your hand or just yell at me. Quiet. Let me keep going. So molecular models, pretty much everyone did a really good job on this one. That pretty much everyone got all the models right. The only thing that was a little confusing was the fact that I wanted the shape of the atoms in the molecule, not the electron groups. So the only change was down here for SF4. SF4 has a free set of, there's a lone pair here. And so we don't see that in terms of the atomic, or the molecular shape. In terms of the shape, how the atoms are arranged, we don't see that. So it's not a trigonal bipyramidal, it's actually a seesaw.
Just one question, Mr.
Yeah.
LeBlanc.
Yeah.
So for the pre-lab, right? I think we touched on this a lot earlier, but so what are we supposed to be turning in again? You just said anything that's kind of like helping you set up for the lab, or what was it again?
Yeah, basically people can just submit what table they're going to use. So that was like really the only thing in the pre-lab was just make the table. That was all.
That's just the okay, got it, gotcha.
Because there weren't any pre-lab questions. There's post-lab questions, but there weren't any pre-lab questions. So that's
gotcha.
that's sufficient.
Okay, thank you.
Yeah.
So is there anything specific you wanted us to submit, or is it just generally going over everything?
In terms of submit for what exactly?
The pre-lab, because it says to submit assignment, but I wasn't like 100% sure what you wanted us to turn in.
Oh yeah, you just the table is enough. Because there isn't any pre-lab questions. So if you just
my table's
your
filled
table
now,
looks like.
so do you want me to just like my
sorry?
table's kind of filled now.
Oh, you did it. You finished? Oh,
I'm in the process.
That's fine. Yeah, you can. Yeah, that's okay. I mean, I realized. Yeah, this first example is going to be kind of crazy, and I didn't even get out a procedure to you until like yesterday. So I'm not worried too much about the pre-lab for this one.
For pre-lab, I just went all the way down in the manual and did those questions, but I guess I'll send the table.
I'll pretty much accept anything for the pre-lab for this one. Don't worry about it. It's the lab report I'm really going to be grading.
Gotcha.
Yeah. Any questions about the test? I can't remember who asked me about the test this morning, but they wanted me to go over it. Did I answer your questions if you're still here?
Yes.
Okay. So you should have all these done by. I graded all mine. The rest should be done like by the end of the week. And you all did really well. I think the lowest mark I've seen so far is like about a 70 or something. Most people got the 80s and a few in the 90s. So great job. So if there isn't any other questions, I got a few more minutes before my voice gives out entirely. Is there anything else people wanted to go over?
For the graph for this lab, we don't need to include the mass of the calorimeter and the mass of the calorimeter plus water, right?
No, because the mass of the calorimeter is not given. So
okay.
So yeah, we don't know what it is. Yeah, the reason for that in the original lab was you were to measure the mass of your coffee cup calorimeter and then pour, I think it was like 50 mils of water in, but to get the exact mass of the water, since you can't really measure, you can measure 50 mils like okay, but you can measure the mass much more accurately. So instead of just assuming you had 50 grams because you had 50 mils, you could actually measure the mass of the coffee cup plus the water and get a precise mass for the water. That was really the only reason for doing that. But because in the simulation we can simulate the precise mass of the water, we don't need to go through that. Any other questions before we wrap things up for today? Oh, remember, if you have any questions, reach out on Canvas, reach out on email. If you want to set up a face-to-face meeting to go over something, we can do that, okay? Because like I've told everybody else, I'm going to be home, and so will you most likely. So if you need any help like that at all, just don't hesitate to ask.
It'll be hard for you to think of an excuse.
Yeah. Yeah, I might be down. I might be out walking the dogs. That's pretty much it.
Can you go over how to find the calculated specific heat again?
Oh, sure. Let's. Need to get my mouse back. Oh, here we go. Okay, this one's not all marked up. Can everyone see that slide?
Yeah, I see it.
Okay. So when we're calculating Q, we are using the water in order to determine that. And the reason is we know the specific heat of water, that's 4.186 joules per gram Kelvin. We've measured.
And that's your C? Sorry.
That's C. That's what C stands for. Yeah.
Gotcha. All right.
So that's that. We know the mass because we measured the mass. So we measure that in grams, right? And we measure the change in temperature.
Then in this case, since in this lab, the mass in grams would be the metal?
No, mass in grams is the water.
Oh, okay.
Because remember, there's two parts of this equation. Because remember, the Q water
equals Q metal. Okay,
negative
gotcha.
Q metal.
Negative Q metal? Okay.
So we calculate Q water because we know what we can measure everything. We know what the values of everything is. We know the value of C, we know the value of M for the mass, and we know the value of delta T because we've measured the change in temperature. So we know all of those. So we measure Q water. That's what we calculate, Q water. Using this as our heat capacity, grams of water, change in temperature of the water. And this is positive, remember, because it goes up. So now that's given us Q. And so Q for the metal will be exactly the opposite. So if my Q water is like 19,000, my Q metal is negative 19,000. Then I go back, so my negative 19,000 joules equals C, which I don't know, times the mass of the metal, which is like, let's say it's 50 grams, times the change in temperature of the metal, which let's say it's like minus 170 K. So then the negatives cancel out, and then we just divide the 19,000 by 50 grams and 170 K. And that gives us C, because remember, C is heat capacity, which is in joules over gram Kelvin, which is what we've got here. We have joules over grams Kelvin. So that's how we so we calculate Q for water first, and then we use that to give us our Q metal, which will be the same and opposite. And then from there, we use those numbers to give us a number for the heat capacity.
Mm.
Is that clear?
Yeah, I think so. Yeah.
Okay. Yeah, I think a lot of people sort of missed that, but I think I may have gone a little too quickly. Like,
Can you stay on this?
you need
Can
to
you stay on the
calculate
slide?
Q. You know, you need to
Can you stay on the
calculate
side?
Q. Yes. Oh, can I
Sorry.
talk about
Yeah,
the
can you stay on
signs?
this slide really quick? I just want to copy the notes. Okay, thank you.
Oh, I see. Yeah. So calculate Q. That will be a number in joules.
Mm.
And you use that number then to go backwards and calculate the specific heat of the metal. Because everything in this experiment is a known except the specific heat of the metal. That's the only unknown. Everything else is either selected or calculated.
But the lab itself, like the website that we're using, it already shows us the specific heat capacity of the metal, right?
Yeah, your calculation better agree with it.
Gotcha. Okay.
So I need you to show me your calculation.
So that's where the 100% no error.
That's right. Because because if you just, if you calculate what Q is and then just, give the heat capacity, and then I do the calculation and it comes out totally different, then I know you just wrote down whatever the heat capacity was rather than calculating it. But yeah, since it's all done, in silico, as it were,